In this module, we're going to talk about experimental designs, and in particular, we're going to focus on different kinds of designs that one can employ to make inferences about the relationship between brain activities and tasks and behaviors. Let's start with some definitions. Designs are characterized by how many independent variables, factors or variables will be manipulated, and what the levels are, the values that each of those factors can take on. Another consideration is how different levels of the factors are sampled and what kinds of measured variables are going to include to help explain behavior or performance or brain activity. Secondly, there's considerations of trial structure, how the events are organized in time into blocked, event-related, or mixed partial trial designs, rapid or single trial designs. We're going to talk about those aspects later. Now I'm just going to focus on the big picture view of kinds of designs that we can use to make different kinds of inferences. So here are several kinds of designs that are commonly employed in fMRI experiments. Subtraction designs are basic contrast between task and control, or one type of task and another. Individual differences designs focus on correlations with external measures of behavior, like age or performance. Process overlap and dissociation designs focus on multiple subtractions, comparing a type of event with multiple types of control conditions, for example. Factorial designs, or ANOVA designs, organize multiple types of events into factors. And finally, parametric modulation designs look at performance or task-related effects within subjects. We'll see examples of each of these kinds of designs in the following slides. The nice thing about these is each of these can be handled by the general linear model. And so there are corresponding techniques that we can do in analysis that go with each of these different kinds of designs. There are also other kinds of designs and design considerations that can't necessarily be handled by the general linear model, and these are considerations for more advanced designs. We'll talk more about these in part 2. And these include things like designing experiments for mediation, or for functional connectivity, or for classification and machine learning analysis. Before we go into the different kinds of designs, here's a really important principle, and it's a basic trade-off. And the trade-off here is between designing a study that is really powerful and efficient for one purpose and designing an experiment that can serve many purposes. So the first I'll call the ideal form design, and this goes back to Plato, who thought that there was one ideal canonical form for each kind of object or thing. In an ideal form type of design, we have few conditions and contrasts. Ideally, two conditions that we're interested in comparing with maximal power. So we have lots of power, we're focusing only on that one comparison, and we have less generalizability and less specificity. We can't do many kinds of comparisons to triangulate on what's really happening. The other kind of design I'll call the Swiss Army knife design. And this is one in which we have many comparisons, many different conditions, and there's high potential for making specific inferences. However, there's very low power. So my strong recommendation is, if you're just starting out, if you're doing your first studies in a new area or field where you don't know how strong the effects are, where they are, how easily you can get them, then stick with the ideal form design. Once you've done this a number of times and you really are ready to take the next step to increase the specificity of your inferences about brain and behavior relationships, then go to more of the Swiss Army knife design. And do that with caution. Let's remind ourselves first about the hierarchical data structure, which is going to constrain how we think about designs. So if you remember, there are voxels within images. Images are sampled over time within runs within sessions, and sometimes multiple sessions per subject. Now I've got multiple subjects nested within a group, and sometimes even multiple groups. So there are two basic kinds of variables in a design. The first is within-person variables, and those are ones that are manipulated across time or trials, so each person serves as their own control, and each person experiences both types of events, or all levels within a variable. So one example is word type in a language study. We might look at nouns and verbs, and every person sees both nouns and verbs at some time during the experiment. The other kind of variable is called a between-person variable. And these are person-level characteristics with one value per person. So examples are age, overall test performance or IQ, maybe even group identity, like are you a patient or a control? So in the table you're about to see in a second, which is the rows are at the top, we can characterize a number of types of designs by which variables they typically include or contain. So the designs are characterized by the number and arrangement of those within-person and between-person variables, and also whether those variables are experimentally manipulated or simply observed or just measured. So here are within-person variables, and we'll look at how many factors there are, where a factor would be something like word type, concrete abstract, stimulus type, how many levels those factors have, and how many observed within-person variables have. Like people's natural performance is an observed variable within person, performance from trial to trial. Here are the between-person factors, and these include how many factors, what are their levels, patient and control would be 2 levels, and how many between subjects variables are we observing but not manipulating, like performance. And here's an overview then of what a number of these different kinds of designs look like in terms of their characteristic variables. So a simple subtraction design, to focus on the first row, will have one within subject factor with 2 levels. Task A minus B, task versus control. A multiple subtraction design might have at least one within subject factor, but multiple levels for multiple comparison conditions. A factorial repeated measures design has at least 2 factors that are independent and at least 2 levels per factor. A parametric modulation design is one in which at least one within-person factor is observed or manipulated with many levels, usually. A brain behavior correlation design is one in which at least one between-person variable is observed. And a case control design, this would be a patient versus control, is one in which at least one between subject factor is present with at least 2 levels. So let's look at examples of each of these types of designs. Here, in a subtraction design, the basic idea is to compare task A versus task B. And often, if we manipulate the task, we can have a better shot at making valid causal inferences about the brain activation that ensues. So in our example here, we're interested in comparing what happens when people look at negative pictures, aversive pictures like you see here, and in condition B, they just look at the pictures. In condition A, they look at them and they engage in a reappraisal process, rethinking that picture, what it means to them in a way that makes it less bad. So they might see that snake and go, oh, I think snakes are really fascinating animals, they're really cool, they're not very dangerous. And then people end up feeling better. So that's the reappraise condition. We also, in this example experiment, we also included another condition, which is just looking at neutral objects. So we'd like to know where the reappraisal activity is in the brain. What's happening? Where's the reappraisal action? And to use this kind of design to infer that requires making some assumptions. And the basic assumption goes way back to the 1800s. It's called pure insertion. And this is the idea that I can compare more complex conditions to simpler ones by simply subtracting off the activity due to the simpler condition. And whatever's left over must be related to the more complex condition. So here, my assumption plays out in this way. I'm going to assume that looking at neutral pictures engages a lot of neutral picture-related processing, visual processing and semantic processing and so on, and that looking at an aversive picture has all that stuff to the same degree plus the negative emotion component. If that's true, I can subtract C from B and end up with where's the negative emotion. Now I'm going to take looking at negative pictures, aversive pictures, and I'm going to add to that the reappraisal demand. So I'm assuming again that the negative emotional components and other features of the stimuli are matched or the same, and I can subtract them off, and what's left when I subtract A minus B is the activity related to the reappraisal. And there are many issues with this kind of subtraction logic. And this is a really nice paper by Friston and others that outline some of these problems. But it's still a quite useful kind of design. Some of the problems are that the processes that I'm interested in might interact with context. The object recognition may not be the same if it's an aversive picture or a neutral picture. We can test some of these things with factorial designs that we'll see later. So pure insertion is often violated, but it can still give us a useful bread and butter test for isolating activation, which is potentially related to particular psychological effects that I care about. Let's look now at correlations with individual differences. And this is one way of increasing the specificity of the inference that I'm making. So we'll stick with our reappraise versus look example. And here, what we're interested in is using brain activity to predict or correlate with the drop in negative emotion that people feel. So first we'll take the comparison, reappraise minus look, that's A versus B in brain activity at each voxel. And then we'll take the drop in negative emotion that people feel when they reappraise versus look. And we're going to correlate those two things. So we're going to ask, where in the brain do the subjects with more reappraisal-related activation show larger decreases in negative emotion? And that looks like this. In this study, there turns out to be correlations across many areas of the brain. And you can see one in the ventrolateral prefrontal cortex there, where the greater the increase in the brain response to reappraise versus look negative, the greater the reappraisal success or drop in negative emotion. That's a basic brain behavior correlation. And it gives a stronger idea that this brain area is really related to performance in some way.